Our galaxy, the Milky Way, is a spiral island of billions of stars, vast and seemingly serene. Yet, at its very heart, lies an enigma, a cosmic leviathan whose gravitational pull is so immense, not even light can escape. This is no ordinary star, no nebula, but a supermassive black hole, Sagittarius A, the silent architect shaping our stellar home. Its presence defines our galaxy in ways we are only just beginning to comprehend, a true monster at the heart. For centuries, the true nature of our galaxy's core remained veiled, obscured by thick clouds of gas and dust. What lay behind this cosmic curtain? Modern astronomy, peering through these galactic shrouds with infrared and radio telescopes, began to uncover something extraordinary. Not a dense cluster of stars, as once imagined, but an empty void, a region of immense mass compressed into an infinitesimally small space, influencing everything around it. The concept of objects so dense gravity traps even light was first theorized centuries ago by figures like John Michell and Pierre Simon Laplace. But it was Einstein's theory of general relativity in the early 20th century that provided the rigorous mathematical framework. His equations predicted extreme warps in spacetime caused by massive objects, leading to the theoretical existence of black holes, singularities where matter collapses infinitely. Observations in the 1960s provided the first compelling evidence for celestial black holes. X-ray emissions from Cygnus X1, a binary star system, suggested a compact, unseen companion drawing matter from a visible star. The immense energy released as gas spiraled into this invisible object became a signature of accretion, distinguishing it from other astrophysical phenomena. Yet these were stellar mass black holes, formed from the collapse of individual giant stars. The idea of supermassive black holes, millions or even billions of times the mass of our Sun, residing at the hearts of galaxies, was a far grander concept, emerging later as evidence accumulated for extremely energetic galactic nuclei. The first hint of a supermassive black hole at the Milky Way's center came from observations of strange radio sources in the constellation Sagittarius in the 1930s. Carl Jansky, a Bell Labs engineer, detected persistent radio noise from this direction, later identifying it as coming from the galactic core. This unseen emitter was named Sagittarius A. Decades later, in the 1970s, detailed radio maps showed a very compact, non-thermal radio source right at the presumed center of our galaxy, distinct from the surrounding nebulae. This extraordinarily bright and compact object, now called Sagittarius A, where the asterisk denotes its active nature, was unlike anything seen before. Its emission properties hinted at an extreme environment. The true breakthrough in understanding Sagittarius A came with the observation of stars orbiting astonishingly close to this invisible object. Astronomers, using adaptive optics on large telescopes, tracked individual stars in the galactic center over decades. Their unbelievably fast, tightly bound orbits provided irrefutable evidence of an immense, compact mass. One star in particular, S2, became crucial. Its orbit, traced for over 16 years, completed a full revolution around Sagittarius A from its rapid movement. Astronomers calculated the central object's mass to be over 4 million times that of our Sun, confined within a region no larger than our solar system. This incredible density could only be a supermassive black hole. So what exactly is a black hole? It's not a hole in the traditional sense, but a region of spacetime where gravity is so strong that nothing, not even light, can escape. This boundary is called the event horizon. Beyond it, all paths lead inward, towards an infinitely dense point known as a singularity. While we cannot directly see the black hole itself, we can observe its powerful effects on its surroundings. The intense gravitational field of Sagittarius A accelerates gas, dust, and stars to extreme velocities, heating them to millions of degrees as they approach, causing them to emit powerful X-rays and radio waves. The density required for such immense gravity is staggering. If our sun were compressed into a black hole, it would be only a few kilometers across. Sagittarius A packs 4 million solar masses into a region roughly 26 million kilometers in diameter, barely larger than Mercury's orbit. It's an unimaginably compact cosmic titan. The supermassive designation isn't just about size, it's about genesis. While stellar black holes form from collapsing stars, supermassive black holes are thought to grow through a combination of mechanisms. They might begin as seeds from early universe collapses, then gradually accumulate vast amounts of gas and dust, and even merge with other black holes. One leading theory suggests that the first supermassive black holes formed directly from the collapse of massive primordial gas clouds, bypassing the stellar phase entirely. These direct collapse black holes would have provided the initial gravitational anchors around which early galaxies could then assemble. Alternatively, some propose they grew rapidly from the remnants of the very first massive stars. Regardless of their initial spark, the common thread is their prodigious appetite, consuming surrounding matter over billions of years, gradually swelling to the gargantuan proportions we observe today. Understanding Sagittarius A is akin to understanding the engine room of our galaxy. Its enormous gravitational influence extends far beyond its immediate vicinity, affecting the orbits of stars and gas clouds throughout the galactic bulge. This region, teeming with stars, is dynamically shaped by the black hole's presence. Within just a few light-years of SGR-A, stars orbit at truly mind-boggling speeds, hundreds or even thousands of kilometers per second. This extreme motion creates a unique astrophysical laboratory, allowing us to test Einstein's theories of gravity under the most intense conditions imaginable. Observations of S2's orbit, for instance, showed a subtle shift in its periapse, the point of closest approach to the black hole, that precisely matched the predictions of general relativity. This precession is a powerful cosmic confirmation of Einstein's theory on the largest scales, a gravitational dance exactly as predicted. The region immediately surrounding Sagittarius A is not a calm void. It's a chaotic, highly energetic environment. Superheated gas, stellar winds, and supernova remnants collide and interact under the influence of the black hole's immense gravity. Despite its monstrous mass, Sagittarius A is considered relatively quiet compared to the active galactic nuclei found in distant quasars. Our black hole only occasionally flares up, consuming small amounts of gas. If it were truly active, the galactic center would be bathed in scorching radiation, making life impossible. The quiet nature of Sagittarius A means it's not constantly gobbling up vast amounts of matter. Its accretion rate, the speed at which it consumes infalling gas, is surprisingly low. This is partly because there isn't a continuous, abundant supply of cold gas falling directly onto it. Instead, the black hole is starved. Most of the gas and dust in the galactic center is in stable orbits or ejected by stellar winds. Only occasional gas clouds or a small star wandering too close are captured, leading to transient flares of X-ray or radio emission. One intriguing discovery is the gobjects, enigmatic gas and dust clouds that orbit Sagittarius A as if they were solid objects, yet they get stretched and heated by the black hole's tidal forces. They represent a new class of objects, perhaps a star hidden within a dense cocoon of gas and dust. When these gobjects approach Sagittarius A, the powerful tidal forces stretch and pull them apart, heating their gas to millions of degrees. This process can cause the black hole to briefly burp out X-rays and other forms of radiation, providing a glimpse into its occasional feeding habits. Beyond the immediate vicinity, Sagittarius A plays a crucial role in the evolution of the entire Milky Way, particularly in its formation and the shaping of its central bulge. It provides a gravitational anchor, influencing the overall density and distribution of stars. Early in the galaxy's history, the black hole's powerful gravitational well likely played a role in attracting large amounts of gas, which then collapsed to form the dense stellar population of the galactic bulge. This central region is significantly older and more crowded than the spiral arms. The formation of the central bar, a prominent feature of our galaxy's disk, might also be subtly linked to the supermassive black hole. While direct evidence is ongoing, simulations suggest the black hole can influence orbital resonances that contribute to bar stability and growth. Even though Sagittarius A is currently quiescent, in the past, it may have been far more active. Evidence suggests our black hole previously had powerful outflows or jets, similar to those seen in active galactic nuclei, potentially influencing star formation in the outer regions of the galaxy. These ancient jets, if they existed, could have caused immense shockwaves, heating gas, and potentially triggering or suppressing star formation on a galactic scale, shaping the galaxy's development in profound ways that we are still trying to unravel. Moreover, the existence of a supermassive black hole at the center provides a stabilizing influence on the galaxy's rotation. Without this immense gravitational anchor, the stellar disk of the Milky Way might be more prone to instabilities, potentially affecting its long-term structure. The discovery of a population of young, massive stars in the immediate vicinity of Sagittarius A poses another puzzle. These S-stars are relatively new, yet they are extremely close to the black hole, a region where star formation should be inhibited by intense tidal forces. How do these young stars form so close to a supermassive black hole? One theory suggests they didn't form in situ, but migrated from further out, perhaps from a massive stellar disk. Another proposes a different, more exotic scenario, involving the collapse of gas clouds under unusual conditions. The environment around Sagittarius A is also a unique laboratory for studying extreme physics. The immense gravitational field creates conditions unlike anywhere else in the galaxy, affecting everything from stellar orbits to the behavior of light itself. The Event Horizon Telescope, an international collaboration of radio observatories, has recently provided the first image of a black hole, not Sagittarius A itself, but the supermassive black hole in the galaxy M87. This groundbreaking achievement gives us unprecedented insight into these cosmic behemoths. While not of our own black hole, the M87 image confirms theoretical predictions about black hole shadows formed by light bending around the event horizon. It's a testament to our understanding of general relativity and a precursor to future, even more detailed images of Sagittarius A. The Event Horizon Telescope has been actively observing Sagittarius A for years. Although its data is more challenging to process due to our black hole's dynamic nature, scientists anticipate revealing its shadow soon. This will allow for direct comparison with M87 and further refine our understanding. Looking ahead, future missions like the Square Kilometre Array and gravitational wave observatories promise even deeper insights into Sagittarius A gravitational waves. Ripples in spacetime caused by extreme cosmic events offer a completely new window into black hole mergers and dynamics. While Sagittarius A is quiet now, its future activity is not entirely predictable. Galactic mergers, where the Milky Way collides with other galaxies like Andromeda, could provide a fresh supply of gas, reigniting its active phase and transforming our galaxy's core into a luminous quasar. Such a merger would be a slow, cosmic dance spanning billions of years, but eventually, the two supermassive black holes would spiral towards each other, culminating in a colossal gravitational wave event as they coalesce into an even larger black hole. The impact of Sagittarius A transcends its gravitational pull. It is a cosmic constant, a fundamental component of our galaxy's identity, influencing its birth, growth, and destiny. Its presence reminds us of the universe's powerful and mysterious forces at play. From the earliest observations of faint radio signals to the precise tracking of individual stars, our journey to understand Sagittarius A has been a testament to human ingenuity and perseverance. Each piece of evidence paints a clearer picture of this colossal cosmic engine. The study of Sagittarius A allows us to probe the most extreme physics, testing the limits of our understanding of gravity and spacetime. It pushes the boundaries of general relativity and provides clues for theories that attempt to unify all fundamental forces. The mystery of how supermassive black holes form and evolve alongside their host galaxies is a central question in astrophysics. Do galaxies form first, then grow their black holes, or does the black hole dictate the galaxy's development? This coevolution is a complex cosmic dance. Observations seem to indicate a tight correlation. The more massive the galaxy's bulge, the more massive its central supermassive black hole. This implies a profound symbiotic relationship, suggesting that these monsters are not just passengers, but active participants in galactic evolution. The feedback mechanisms between the black hole and its host galaxy are still being actively researched. Outflows from the active black hole can heat and expel gas, preventing further star formation, thus regulating the galaxy's growth. Alternatively, some simulations suggest that black hole activity can also compress gas, paradoxically triggering bursts of intense star formation. It's a delicate balance, dictating the galaxy's star-forming history and overall morphology. The vast distances to the galactic center, coupled with obscuring dust and gas, make it an incredibly challenging region to study. Every observation, every piece of data, represents a triumph of astronomical engineering and data analysis. Despite the challenges, the past few decades have yielded unprecedented progress, largely due to advancements in infrared and radio astronomy, which can penetrate the obscuring dust that visible light cannot. The sheer number of stars in the galactic bulge, estimated to be more than 10 billion within the central few thousand light-years, creates a dynamic environment in which Sagittarius A resides, constantly supplying it with potential infalling material. Our understanding of supermassive black holes is not limited to Sagittarius A studying distant quasars, which are extremely active galaxies powered by their central black holes, helps us understand the extreme end of black hole behavior and evolution across cosmic time. These observations of highly active black holes in the early universe suggest that supermassive black holes grew very rapidly, very early on. This poses a challenge to understanding how such immense structures could form so quickly after the Big Bang. Models for rapid black hole growth involve processes like highly efficient accretion, eating matter very quickly, or the direct collapse of massive gas clouds into black holes, bypassing the stellar phase, as mentioned earlier. The discovery of intermediate mass black holes filling the gap between stellar and supermassive black holes suggests a possible pathway for their growth, perhaps through repeated mergers of smaller black holes, eventually leading to the supermassive class. Every galaxy we look at appears to harbor a supermassive black hole at its core. This universality suggests that these monsters are not mere cosmic accidents, but an integral, perhaps even necessary, part of galactic structure and evolution. The gravitational waves detected by instruments like LIGO and Virgo have opened a new observational window into the universe, allowing us to hear the cosmic symphony of black holes merging, confirming another key prediction of general relativity. While these detections primarily involve stellar mass black holes, future gravitational wave observatories, like LISA, will be sensitive to the much larger waves produced by merging supermassive black holes, offering direct evidence of galactic mergers and the growth of supermassive black holes. The study of Sagittarius A and other supermassive black holes is not without its tantalizing mysteries. For instance, the origin of powerful cosmic rays, highly energetic particles that constantly bombard Earth, might be tied to active galactic nuclei. Another ongoing mystery is the spinning of black holes. While difficult to measure directly for Sagittarius A black hole's spin influences the shape of its event horizon and the potential for it to launch powerful jets. The very edges of the event horizon, where spacetime is most distorted, remain a frontier of theoretical physics. What happens to matter as it crosses this point of no return? While we cannot know directly, theoretical models continue to refine our understanding. The extreme environment near Sagittarius A also allows us to explore quantum gravity, the elusive theory that seeks to unify general relativity with quantum mechanics. Under such immense gravitational fields, quantum effects might become observable. The immense power of Sagittarius A is a stark reminder of the universe's capacity for creating structures of unimaginable scale and density. It dwarfs our sun, our solar system, and even entire star clusters. Despite its awesome power, its relative quietness now means Earth is safe from its immediate destructive effects. We are located far enough away, some 26,000 light-years, to be outside its most violent influence. However, its history of activity means that our galaxy has undergone periods where its core was a far more energetic and hazardous place. The echoes of these past burps are still visible in the form of colossal, faint structures like the Fermi bubbles. These immense gamma-ray and X-ray emitting structures, stretching tens of thousands of light-years, are believed to be remnants of a massive outflow from Sagittarius A millions of years ago, when it was much more active. Studying the Fermi bubbles helps us piece together the past life of our supermassive black hole. They represent a massive energy injection into the galactic halo, impacting the gas and magnetic fields in our galaxy's outer regions. The weather at the galactic center is constantly changing, driven by events like stellar supernovae, which can send shockwaves and gas clouds spiraling towards Sagittarius A, occasionally feeding the cosmic monster. Future generations of telescopes, both ground-based and space-based, will continue to refine our understanding of Sagittarius A's immediate surroundings in unprecedented detail, revealing objects currently hidden by obscuration or resolution limits. For example, the dynamics of dark matter, the mysterious invisible substance that makes up most of the galaxy's mass, could be subtly influenced by the immense gravity of Sagittarius A in its halo. The search for fundamental physics beyond the standard model also finds a laboratory at the black hole's edge, where extreme gravity and energy might reveal new particles or interactions that are not observable in terrestrial experiments. The very existence of Sagittarius A challenges our intuition. It embodies the universe's capacity for paradox, a region of infinite density that profoundly shapes what appears to be empty space. It's a reminder of how much we still have to learn. The black hole's influence isn't limited to larger-scale structures. It can even affect individual stars. Stars orbiting too close, like the S-stars, experience extreme tidal forces that can stretch them into elongated shapes or even rip them apart. Such tidal disruption events lead to spectacular flares of radiation as the star's material is heated and devoured by the black hole, offering astronomers a rare glimpse into the black hole's feeding habits. The density of stars in the galactic center is astounding, millions of times greater than in our local neighborhood. This creates a fascinating environment for star-star interactions, mergers, and binary systems. Some theories suggest that the runaway collision of stars in this dense region could lead to the formation of some of the massive, young stars found near Sagittarius A, or even create other intermediate mass black holes. The dark matter spike hypothesis suggests that dark matter might accumulate in a denser concentration around supermassive black holes. If true, this could offer a unique opportunity to directly detect dark matter through its annihilation signals. Gamma-ray telescopes are actively searching for these signals, which would be extremely faint but distinct. The potential discovery would revolutionize our understanding of the universe's most elusive component. The precise distance to Sagittarius A is crucial for understanding galactic structure and dynamics. Using various methods, astronomers have triangulated its distance with increasing precision, placing it consistently at around 26,000 light-years from Earth. This precise distance allows us to accurately calculate the black hole's mass from the orbital periods of the S-stars, solidifying the evidence for its supermassive nature without relying on assumptions about its composition. The gravity turn near the galactic center, where stars transition from the relatively flat orbits of the disk to the more chaotic and inclined orbits of the bulge, is also subtly shaped by the supermassive black hole. The galactic center is a source of high-energy neutrinos, elusive subatomic particles created in extreme cosmic events. These neutrinos could originate from particle acceleration near Sagittarius A, offering another probe into its powerful processes. The study of Sagittarius A is an interdisciplinary field, combining observations from infrared, radio, X-ray, and gamma-ray telescopes, along with theoretical modeling and numerical simulations. It's truly a converging point for astrophysics. The future of galactic center astronomy promises even more astonishing discoveries. The next generation of telescopes, like the James Webb Space Telescope and the Extremely Large Telescope, will peer into this region with unprecedented clarity. The James Webb Space Telescope, with its unparalleled infrared sensitivity, will unveil even more details about the stars, gas, and dust close to Sagittarius A, allowing us to study the processes occurring in this extreme environment with new eyes. The Extremely Large Telescope, with its enormous mirror and adaptive optics, will allow for even more precise measurements of stellar orbits, pushing the boundaries of general relativity testing and looking for subtle deviations. Ultimately, Sagittarius A is more than just a cosmic behemoth. It's a fundamental piece of the cosmic puzzle, a living laboratory where the most extreme forces in the universe play out, shaping the very fabric of our galaxy. Its study helps us answer fundamental questions about our place in the universe, the origins of galaxies, and the ultimate fate of cosmic structures. It connects us to the grand narrative of cosmological evolution. From the smallest subatomic particles to the largest superclusters of galaxies, the universe is a tapestry woven with fundamental laws. Sagittarius A provides a unique thread in this tapestry, demonstrating gravity's ultimate power. The ongoing quest to fully understand our galaxy's central monster is a journey into the heart of darkness, yet it illuminates our understanding of the cosmos in brilliant and unexpected ways. The gravitational pull of Sagittarius A warps not just spacetime, but even the perceived flow of time near its event horizon. For an observer falling in, time would appear to slow infinitely for external observers, a truly mind-bending effect. This time-warping effect, predicted by general relativity, is theoretical for black holes, but has been precisely measured for less extreme gravitational fields, such as those caused by Earth itself and its immediate satellites. The environment around a black hole is not only gravitationally extreme, but also electromagnetically dynamic. Strong magnetic fields thread through the accretion disk, influencing how matter falls in and out. These magnetic fields are thought to be responsible for launching the powerful jets seen in active galactic nuclei. They act like colossal cosmic slingshots, expelling superheated plasma at relativistic speeds away from the black hole's poles. Even though Sagittarius A does not currently display powerful jets, there is evidence of faint, diffuse X-ray emission extending along its rotational axis, possibly indicating remnants of past, more powerful outflows or a weaker current outflow. The mass measurement of Sagittarius A relies heavily on Newton's laws of motion applied to the stars orbiting it. The incredibly precise observations of S2 and other S stars are crucial for pinning down this value. These measurements of stellar orbits offer a truly unique confirmation of Einstein's general relativity in a strong field regime where gravity is incredibly intense. It's astronomy's way of testing fundamental physics. Astronomers are also searching for intermediate mass black holes within the galactic center itself. These missing links could be the seeds for supermassive black holes or the remnants of smaller galaxies consumed by the Milky Way. Such discoveries would provide invaluable data on how black holes grow through mergers, a process believed to be significant for the largest supermassive black holes observed in the universe. The Galactic Center is a laboratory for studying the interactions between stars, gas, and dark matter under extreme conditions, offering insights into processes that are impossible to replicate in our comparatively serene solar neighborhood. The starburst region within the central parsec of the galaxy is a zone of intense star formation, where new, massive stars are constantly being born. This activity feeds the black hole with gas and stellar winds. These massive stars have short, brilliant lives, ending in spectacular supernovae that enrich the galactic center with heavy elements, impacting future star formation and the very composition of the region. The gas and dust in the galactic center are subject to powerful radiation fields from all these massive stars and the black hole itself, leading to complex chemical reactions and molecular diversity that are unique to this region. The Milky Way is not alone in harboring a supermassive black hole. Almost every large galaxy studied to date appears to have one, reinforcing their fundamental role in galactic evolution and structure. The relationship between a galaxy's black hole and its host is often described as a coevolution. They grow and influence each other over cosmic timescales, a cosmic dance of mutual shaping. The study of Sagittarius A allows us to piece together the history of our own galaxy, tracing its growth, its periods of chaotic activity, and its eventual settling into the majestic spiral we see today. Its existence prompts us to reconsider familiar concepts of space and time. Where gravity becomes so overwhelming, our everyday notions of reality break down, replaced by the profound predictions of Einstein. The profound influence of Sagittarius A extends to the fate of our galaxy. Its presence dictates the ultimate destination for any star or gas cloud that ventures too close to the galactic core. The continued growth of Sagittarius A, slow as it is now, ensures its status as a permanent, growing fixture at the heart of our galaxy, a cosmic anchor throughout its vast lifespan. The research around Sagittarius A is a testament to humanity's insatiable curiosity. From earthbound instruments to space telescopes, we continuously push the boundaries of technology to reach further into the cosmos. As we develop more sensitive detectors and more powerful computing capabilities, our understanding of these cosmic behemoths will continue to deepen, revealing even more unexpected secrets. Our Milky Way, with its central monster, is just one of billions of galaxies, each one a unique cosmic story shaped by its own central supermassive black hole. They are the hidden engines of the universe. The monster at our galaxy's heart is not just an object of scientific curiosity. It's a reminder of the raw, untamed power of the universe, a power that shaped our galactic home and all the stars within it. It stands as a testament to the fact that even the most seemingly empty voids in space can harbor the most profound and influential structures, forever altering the cosmic landscape around them. Sagittarius A is a cosmic mystery gradually yielding its secrets, but each answer only leads to more profound questions, propelling us further into the grand cosmic inquiry. The saga of Sagittarius A is a continuing story, written by dedicated astronomers and physicists, observed by advanced instruments, and interpreted by brilliant minds. It is a testament to humanity's relentless pursuit of knowledge. As we look up at the night sky, knowing there's a supermassive black hole at the very center of our stellar island, our perspective on our place in the universe is forever altered and deepened. It's a humbling thought that our tiny blue planet orbits a star which orbits a galaxy that is ultimately bound by the colossal gravitational grip of a monster at its heart. But it is also an empowering thought that through science and technology, we can peer into these unimaginable depths and decipher the powerful laws that govern them. The monster at our galaxy's heart, Sagittarius A, is not just a destroyer but a cosmic sculptor, a fundamental architect shaping the destiny of the Milky Way and potentially other galaxies across the universe. Its story is interwoven with the story of our galaxy, a silent, powerful presence that continually reminds us of the grandeur and mystery that lie at the very core of our cosmic home. And so, the journey to understand the monster at our galaxy's heart continues, an endless pursuit of knowledge into the universe's most wondrous and extreme phenomena, revealing how it truly shapes everything.